Alright, my goal in this video is to cover basically all of Chapter 5 in a quick, reasonable, hopefully effective way where we can still get some meaningful information here, but I don't want to linger too much on this. Really, Chapter 5 is going to be broken up into a few parts. The first part is what's called the dot product. If you've ever taken a Calc 3 class, the dot product is one of the first things that you talk about in Calc 3. So I apologize if you've taken Calc 3, this will be old news. But the idea is that, let's say I have two vectors in R3. Let's say I have 1, 4, 3, and 2, 1, 0. Okay, these are both vectors in R3. When I don't write subscripts, by the way, these are just vectors relative to the standard bases. And so you can take the dot product of these two vectors. Okay, so 1, 4, 3 dotted with 2, 1, 0. And what this is it's going to give you a scalar. This dot product is going to be, what you do is you multiply the corresponding entries, and then you add all of those up. Okay, so we're going to end up with 1 times 2 plus 4 times 1 plus 3 times 0. So in our case, we get 6. Okay, and that's the dot product. This dot product gives us some nice information about vectors. Namely, it turns out that two vectors this is actually true in general, but two vectors in Rn are orthogonal. Orthogonal is really just another word for perpendicular, but it's the word that mathematicians use. Orthogonal means a straight angle. Okay, so ortho, like orthodontist or orthopedist, is someone that straightens your teeth or straightens your bones, right, if you break your arm or something. And then gon is angle. So these are two vectors that are at a straight angle. So two vectors are perpendicular. It turns out this is going to be true if and only if their dot product, let's actually give these two vectors names. So I forgot to give these two vectors names. So these two vectors, say x and y. They're going to be orthogonal if and only if x dotted with y is 0. Okay, I'm not going to go over the proof of this. The proof is very geometric, naturally, because we're talking about right angles. But anyway, so this is the dot product. And the dot product in R3 is used a lot. There's many things that you use the dot product for. So you can use the dot product when you're trying to figure out what are some things that are, say I have a vector and I want to figure out, is another vector orthogonal to it? What's the plane that's orthogonal to it? What are tangent planes? You can actually use the dot product to compute volumes of parallelepipeds, which are, I'm not going to draw it, but they're three-dimensional analogs of parallelograms. You can do lots of things with dot products. There's lots of uses. A few things that I just want to point out, though. If I were to have a vector, let's say v, it doesn't really matter what vector we use here, but let's say I have a vector v, which is 1, 4, 3. Then if I were to look at the length of that vector, it turns out would be the sum of the squares of the components. So 1 squared plus 4 squared plus 3 squared. And then we take the square root of that. And of course this 1 squared plus 4 squared plus 3 squared we can actually think of as v dotted with v. Okay, so that's the one way to get the length of a vector. Okay, so you just take the square root of the dot product of that vector with itself. Okay. I should point out, by the way, that if you have, I need to think of the best way to write this here, but if I were to have the vector 1, 4, 3, in our case, what we would get would be the square root of, let's see, 1 plus 16 plus 9. So that'd be the square root of 26. And I could think of this dot product in a few ways, but I could think of v dot v as actually, and this is genuinely what the dot product is, but I could think of it as the matrix product of the matrix 1, 4, 3, and 1, 4, 3. Right, so this is really just the matrix product of V transpose times V. Okay, and so you start with a, let's just do a little dimensional accounting here. This is a 1 by 3, this is a 3 by 1. When you multiply them, you end up with a 1 by 1 matrix, which 1 by 1 matrices are really just real numbers, so there's no need for us to write any brackets or anything notationally around them. But v dot v is really just V transpose times V. That's really all it is. And so you get a lot of nice properties from this. You get the magnitude, the length property. We know that, I think this is just worth saying, it turns out, I'm just going to cut to the chase, but it turns out that x dotted with y is the same as y dotted with x. Here, x and y are vectors in Rn. It turns out that there's a distributive law. There's actually two distributive laws, but x dotted with y plus z is the same as x dotted with y plus x dotted with z. If I were to have a constant times x dot y, that's cx dotted with y, or even x dotted with cy. So let's give these names. And finally, if I were to take the dot product of anything with itself, I get something that's greater than or equal to 0. And furthermore, x dotted with x is equal to 0 if and only if, what are all the vectors with 0 length? Well, so if x is equal to the 0 vector. Okay, so it turns out these are the kind of major properties of the dot product. And the dot product is an example of what's called an inner product. Okay, so an inner product is exactly the same idea as a dot product. So the inner product in Rn is kind of our motivation. And so we can lead to what are called inner product spaces. Inner product spaces are really just vector spaces where you can, over these vector spaces, you can define this inner product. And an inner product is something that satisfies these 4 rules, right? If it has those 4 rules, it's an inner product. Okay, and so there's different inner products that we can talk about in different contexts. I think it's useful to see inner products, say, for polynomials. So just to give you kind of another example. So kind of the classic inner product in Rn is the dot product. You can do very similar things with inner products over matrix sets. But I think one that's interesting is if you were to take, so let's say our vector space is P sub n. So this is the set of polynomials of degree at most n. And remember that polynomials are differentiable everywhere, and therefore continuous everywhere, and therefore integrable everywhere. And so let's say I have 2 vectors, in other words, 2 polynomials, f and g. And what I'm going to do is I'm going to define an inner product on them, and we're going to write inner products with this notation. So this left angle and right angle are kind of less than and greater than symbols. But that's our notation for the inner product. And our inner product is, say, let's just integrate over, say, 0, 1. You can pick whatever interval you want. And it's going to be f times g. Okay, and so that's going to be our, inner product that we're going to define over the vector space P sub n. And you can check all of these properties. We can just check that if I were to take the inner product of f and g, that's the same as the inner product of g and f, right? If I switch the order of the integration, it doesn't change anything. So the first condition is satisfied. If I were to take the inner product of f and g plus h, this would be the integral from 0 to 1 of f times g plus h. If you were to distribute that, you would see very quickly that this is the inner product of f and g plus the inner product of f and h. Okay, so again, I'll leave that details to you if you want to check that anymore. We know that if we were to have a constant times the inner product of f and g, you can write that as a constant times the integral from 0 to 1 of f times g. And you can move the constant in, and you can kind of group it with the f, or you can move the constant in and group it with the g. And so it turns out that this is going to be the same as the integral from 0 to 1 c f of x times g of x dx, or the integral, right, and this, by the way, is c f inner product with g, or you could write this as f times c times g dx. So you could think of this as f taken inner product with c times g. And then our final property is that it turns out that the inner product of any function with itself, if I were to integrate f squared, so if I were to integrate f squared, this would be f of x squared. That's going to be certainly greater than or equal to 0, because we're integrating over this interval from 0 to 1. We're integrating a non-negative function, and moreover, this integral is going to be equal to 0 if and only if f is the 0 vector, right? If and only if f is the 0 polynomial, right? 0x to the n, 0x to the n minus 1, all the way down to 0. Okay, so it turns out that that inner product is going to be 0 if and only if f is the 0 polynomial. So this really is an inner product space. And these are going to be the two big inner product space for us, is the dot product and then this integral inner product over the set of polynomials. Okay. Just two other things to say in this chapter. I really just want to hit the highlights and move on. We're going to say that a vector v in a vector space, well, in a inner product space, so vector v in an inner product space v. Remember that I just want to go up for a second. So remember that when we were talking about inner products, I'm not sure if I explicitly said this or not, but inner product spaces are, these are vector spaces with an inner product. And an inner product is this type of function that we were defining before. But whenever I talk about inner product spaces, we're talking about vector spaces. They're just vector spaces with special properties. So a vector in this inner product space V is going to be called a unit vector. So this is going to be called a unit vector if the magnitude of V is 1. So for example, if I were to take f of x equals, just make this really easy, say x, where I'm thinking of f as being in, say, P2, where P2 has the inner product that we described above, right? The integral from 0 to 1 of f times g. Then the magnitude of f, or the length of f, is going to be the inner product of f with itself, which is going to be the integral of x times x, which is 1/3. Okay, so that means that this inner product is not, this inner product is not a unit vector. Okay, so F is not a unit vector. On the other hand, if I were to look at, say, square root of 3, so f of x is square root of 3 times x, that will be a unit vector because the magnitude of f is going to be the inner product of square root of 3 times x, square root of 3 times x. And then we can do one of two things. We can do two things here. We can bring this square root of 3 outside. That's going to be square root of 3 times whatever this first component was. Oops. So square root of 3x comma x. And then I can do the same thing again with this square root of 3. I can bring that out as well. So I'm going to end up with square root of 3 squared, otherwise known as 3, times the inner product of x with itself, which we just said was 1/3. And so this is going to be 3 times 1/3, which is 1. So f of x being square root of 3 times x, that is a unit vector. Okay. The last topic, just to bring up, and this is related to unit vectors, is there's this notion of what's called an orthonormal basis. An orthonormal basis is going to be a basis where all the basis vectors, so all the basis vectors are mutually orthogonal. What I mean by that is that pick any two basis vectors, they're going to be orthogonal. And each basis vector is a unit vector. So orthonormal bases are the nicest bases that you can possibly work with. And so, for example, when you think about the standard basis in, say, R3, so if you were to look at the standard basis in R3, you'd end up with 1, 0, 0, so I, J, and K. Right, 1, 0, 0, 0, 1, 0, 0, 0, 1. This is an orthonormal basis. So the reason why the standard basis is so nice is that this is an orthonormal basis. Because the magnitude of each of these vectors is 1, right? You would end up with square root of 1 squared plus 0 squared plus 0 squared. So that's 1. Likewise for all the others. And they're all mutually orthogonal, right? When I draw, these are all at a right angle, okay, from one another. So we have our, we have I, J, and K. Okay, so the red, so we have the red vector, the green vector, and then the purple vector. Okay, so that's why those bases are so nice. So that's an orthonormal basis. There's a process, okay, that you can go through. Start with any basis you want, and you can kind of use some geometry to come up with an orthogonal basis. And then once you have an orthogonal basis, you can always just do the trick that we did before of scaling. You can always scale whatever your vector, and you can turn every vector into a unit vector in the same direction. So notice that scaling doesn't change orthogonality, right? If I have two things that are orthogonal, right, if I have two things that are perpendicular, I don't care the scale, right? I don't care if they're really big. I don't care if it's really small, right? If I have two things that are orthogonal, scaling that object isn't going to change orthogonality. So what you do is there's a process where you can start with any basis that you want, and you can arrive at what's called an orthonormal basis, right? These bases that we just described. This process is called the Gram-Schmidt process. Okay, so I'm not going to talk any more about that. This is everything I wanted to say about dot products.